All right, if you're coming in, we still have lots of seats in the interior areas. Probably see 30 or 40 empty seats. Okay, as you can see, some of the details of the College of Engineering's free barbecue lunch for tomorrow, so encourage everyone to come on over, have a free lunch. It's located outside the Harry Reid Engineering Lab, which is sort of next door to the physics building and sort of next door to the chemistry building, in that corner. I could point that way, but that won't help you. So, 11 o'clock to 1:30, hamburgers, hot dogs, ice cream, things like that. So it's free food for college students. It's usually a pretty good deal. Any questions before we get started? All right. If you have questions along the way, we'll try to answer them. Again, like we're usually doing, if you haven't logged in with your clicker yet, please do that. The channel for this room is channel 65, and for the overflow classroom, the channel is 51, if my memory's correct. Brett's over there. He can correct me if I'm wrong. It's written on the podium, Brett. Okay, some quick reminders. Actually, this isn't really a reminder, an announcement. Last class, we did the clickers for the first time. Your grades are posted. If you do not have a grade next to your name and you had your clicker and you were answering questions and all that, what that means is you didn't register your clicker, at least not correctly. We have like the code, like A5, D71, whatever. We have no idea who that is. So you have to register it, and once you do, okay, well, I'm getting a signal that audio in the other room is okay. Once you get it registered, we should be able to go back and fix last week's, but please do that. If you don't get it registered soon, or it's a grace period now, let's put it that way. We want you to go ahead and register it. If you're not sure about how to register your clicker, the instructions are on the website in the course welcome area. It should take you all of 15 seconds, or I don't know, maybe a minute. It's pretty quick and easy, but unless you do that, we get your answers, we just don't know that it was yours, so we don't know who to give the points to, the credit. And if you have any confusion about that, you can see one of the people in the EDL. They might not actually know. You might have to see me during my office hours, which are Monday, Wednesday, Friday in the EDL at lunchtime. Your team charters are going to be coming up due very soon. It's due essentially at the end of the normal business day, or maybe a little later, 6 o'clock p.m. Please keep a copy for your team journal. Your teams should be meeting by now. Hopefully you are. And you will also be working on your journal form entries. The journal forms are essentially a progress report. First of all, it's to help you as a team take a step back from what you just did the last week. Think about whether you met your goals, whether you didn't meet your goals, and what you want to do in the coming weeks. That's essentially what your journal reports are. Those will be done on a weekly basis, except for the 2 weeks where we have holidays in the rest of the semester. I think we have holidays in both cases. 12 of the remaining weeks, you'll be handing in journal forms. And they're fairly straightforward to fill out, and we're going to ask you to attach your meeting minutes from your team when you get together to discuss things to the back of that. After we take a look at it and grade it, we'll be giving it back to you, and you can put it into your 3-ring binders. We're going to ask you to hand in the entire 3-ring binder a couple of times, plus at the end of the semester. Normally, though, on a weekly basis, all you have to hand in is the small stapled packet of your journal form and a copy of your meeting minute notes. So you don't have to carry around a 3-ring binder every week with you. So that's to make it easier for you and easier for the TAs. Otherwise, they come back from class every week with huge stacks of 3-ring binders. So first one will be due, the first addition to your journal will be your team charter, and your first journal will be due in your skills labs next week, starting next Tuesday. If you haven't noticed it yet in the web campus, we have a self-learning module. This is an online set of things to read and practice quizzes that don't actually count any points, but they help you figure out whether you really do get it or not. And at the end of the online module, we have a quiz that really does count for points. So I'd encourage that you take a look at that as soon as you can, really. It has to be done by Monday night of next week. Okay? So this is a little different than you're not actually handing something in, and nor are we covering this stuff in class in as much detail as you need. Dr. Volstead covered a lot of this last class. But you might have thinking, my gosh, this is way too much, way too fast, how to do these calculations and how to interpret all of the results and things like that. We know that it was fast last week. If you've seen it before, then you probably get it and it's not a problem. But if you felt a little bit overwhelmed by it, check out the learning module. 2 of the chapters in the book go into it in detail. This is one of the most, well, it's really the only real calculation you're going to have to do this semester for this class, except maybe batteries, which I'll talk about today. It's probably the hardest one you're going to have to do. And we know that you're not going to be able to get it in a rushed 35 or 40-minute lecture like we did last week. Your teams are starting to get together. Rental kits are going to be available for picking up by your team in the EDL next week. As you did with your course textbook, please pay for it ahead of time. Bring the stamped form over to the EDL, except now you only have to do it 1 per team. So your team in your first meeting might say, all right, who wants to volunteer to do this? And no one will raise their hand, right? And then pick someone to do it. They'll go, they'll take your money, and they'll go and they'll pay for it, and they'll bring it back, and they can go and bring the kits to your next team meeting. Although that said, you won't actually need your kits probably for another 3 weeks or so. The things that are in it, we aren't going to actively use, first of all, until you have clearance to start buying things, and that doesn't happen until your preliminary designs have been approved, and that's not until early October. So that'll be a while. Some of the things in there, like your fuel cells, are not actually going to be in the kits that we hand out next week. We hold on to those fuel cells until the day that we show you how to use them in the skills lab. Okay, so we'll give them to you then. Let's see, journals, as I just mentioned, starting next week. Textbooks, if you haven't paid for it, paid for the rental yet, the deadline hasn't passed yet, don't worry about that, but please try to take care of this as soon as possible. I took a quick look at the list of who's done it, and I think I'd say maybe 80% of the class have already taken care of this. If you're in the other 20%, you don't have to freak out. It's not like you're going to get dropped right now. But please try to take care of that before the drop deadline of the course. And as usual, our assignments are due on certain days of the week. I know I'm starting to sound a little bit repetitive in some of this stuff, but please keep up to date on your reading quizzes, skills lab assignments, and things like that. Generally, if you haven't figured it out yet, most of the assignments in this course are we get into a routine where every week, at least until you're done with a book, every week you have a reading assignment. Every week you're going to have something to do in skills lab. Along the way, we're going to sprinkle in checkpoints, learning modules, and things like that. But there are a couple things that are fairly repetitive. Last week, Dr. Volstead showed you how to do lifting fan calculations, at least a quick introduction to it. You'll see it a lot more in the online learning module that we have. In that, we talked a little bit about the designs or suggestions for how to handle your deck and plenum chamber. But what we're going to talk about today are batteries. We'll get to that in a moment, but a lot of things that we want to cover. Now, the process that Dr. Volstead outlined was an 8-step process for figuring out all of the essential things that you need to know in order to make an intelligent design of your hovercraft. And what that really means when you get down to it is the thing going to hover or not? When I put a certain fan on it with a certain battery, right? That's what you need to know. And if it doesn't, you have to change something in your assumptions, or change something, like use a different fan, use a different battery pack, or something like that. And it becomes an iterative process. You're almost guaranteed to not get your design perfect the first time you try it. Odds are it's either going to be not hovering at all, or it's going to be overkill, where you had 10 fans and you only needed 2. It'll work, but you probably don't want to do that because it's going to kill your budget and it comes out of your pocket, right? So the optimal design in this kind of a situation rarely comes with the first time you do the calculation. So we're going to have you set up all these calculations in a spreadsheet. So all of the formulas will be entered by you into the spreadsheet, and when you want to tweak your design, you just have to change one number. You don't have to redo the whole calculation sequence, all 8 steps over. Actually, I think there's a couple of things you'll have to enter. You have to choose things, and then step down at the bottom here, you have to actually see if such a fan is manufactured by somebody, and if it's in stock, and if it's affordable, and all those things. And if it's not, it might have been technically a good fan to use, but if it's too expensive or unavailable, then you can't use it. You have to redo your design, not because it wasn't good, but because there were practical constraints there. So in a very brief summary, the calculation process involves, first of all, making some estimations and making some choices. Like, for example, you might not know how heavy your hovercraft is going to be. Part of the answer to that, how heavy is your hovercraft, is you need to know how heavy your fan is. But that's the last thing you're doing in this whole calculation, right? So this becomes an iterative process. You estimate the weight. That'll include how many batteries you've got, how many fans you have, what type they are. And you know right up front that is just a guess. You're going to go through this entire calculation sequence and figure out that, all right, well, the fan that I need to use is actually a little bit heavier than it needs to be. So you take the fan that you just ended up calculating, and you enter that weight right back up at the top and go through all of the calculations, and you see whether the thing will still hover after you've done all of your calculations. And if it still hovers at the height you wanted, then you're pretty much done with your calculation. If it doesn't hover, you need to make some changes. And it becomes, in this way, an iterative process where you essentially need to know the answer before you do the calculation. We call this an iterative process because you essentially, you make a guess up front, an educated guess, hopefully. Don't pick that your hovercraft is going to be 30 pounds. It's probably going to be more like 3. So make an educated guess, and you home in, you fine-tune it until your assumptions agree with what you calculated at the very end. So all these 8 steps in the process can get a little bit time-consuming if you do it by hand. So this iteration process, if you do it by hand, is a bit of a pain in the butt. But when you use Excel or some other computer program, the process can be made much more quick when you do this. So I'm not going to go through all of these. The online learning module can do this for you. However, first quiz question or first clicker question. Let's say that you had a fan and you want to compare what it will do compared to having 2 fans on your hovercraft. So a one-fan hovercraft is instead you're being asked to evaluate what would happen if you took 2 identical fans and put them side by side on your hovercraft. If each fan can generate 80 pascals, and this is a metric system version of the inches of water that Dr. Volstead talked about, at a flow rate of 1/4 of a cubic meter every minute. Okay? Actually, I shouldn't use meters. That should say min, not meters. So the question is, when you put 2 side by side, what's going to happen? Is the overall pressure going to double? Will the overall flow rate double? Will both double? Or will nothing happen? So let me know what you think. We did talk about this a little bit during class last week, but we didn't really dwell on it. So you might remember the answer, or you might be able to just use your intuition to this. All right. So the answer is that the flow rate will double, not the pressure. Okay? This is one of the subtleties for how fans work in these things. You can get twice as much air flowing to the bottom side of your hovercraft, but it's really not going to change the pressure very much. The pressure is largely going to be dictated by how heavy your hovercraft is and how large your deck is of the hovercraft. These are nuances for the calculations that you'll learn quite well when you go through all the learning modules and read the chapters in the book. But we did talk about it briefly in class the other day. So that's the first clicker question. So let's move on. So in order to actually run one of our fans on these hovercrafts, we need a power supply, obviously, right? And as it turns out, on your entire hovercraft, it's quite likely that the most power-hungry element that you've got there are going to be your lift fans. So you have to figure out how to effectively power them. And in this class, batteries are the best way to do it. There are a lot of other ways that you can power fans, hamsters or fuel cells or whatever. There's a lot of different mechanisms. You might be tempted to try to power a fan using the fuel cell that we're going to be giving to you. That's going to be pretty challenging. You can get a really wimpy fan to turn with the fuel cell, but it's certainly not going to get you to lift up off of the surface. You could go out and spend a few $1,000s and get a fuel cell that would do the job, but that's probably not well, it's going to blow your budget for one. Okay, so we need to learn a little bit about the batteries that we're going to be working with, because they're really going to be very easy to do overkill on your batteries and very easy to do insufficient amount of power. So you have to know how batteries work, how you can combine them to get the desired voltages and currents and run times for your fans so that you can have a nice and effective hovercraft. It's very easy to know when your system is under-designed because it doesn't hover. When your batteries are not adequate, it just won't hover. Or it hovers for 30 seconds and then it eventually just settles down to the ground as the batteries run dry. Okay? Far more, those are the easy problems to catch. More difficult or more insidious problems are when your batteries are, essentially you have too much of them, too many. People will oftentimes design their hovercrafts and they'll be, we got ours to run for 4 hours. It's like, well, great. Competition runs for 4 minutes. You probably bought 100 times more batteries than you needed to, okay? And you had a lot more weight on your hovercraft than you really needed to design around, okay? So let's look at how we can figure out the batteries a little bit more carefully. So electrical devices will have a voltage at which they run at. They'll require a certain amount of electrical current to run. And the product of these two, the voltage multiplied by the current, is a measure of the power. All right? And when you get into a physics class, if you had physics in high school and you looked at this, you probably studied power at some level. Here at UNR, you'll be studying not only in the electrical engineering courses, but you'll study this in physics. The product of the voltage and the current gives you power, which is the amount of energy that is used per unit time. So it is energy, but it's not just energy. It's how long that energy is needed for. So the product of these is the power. And when you buy a fan, oftentimes, well, first of all, it'll tell you what voltage it can run at. I'll get to that in a second. It's actually some fudge factors. You have some latitude there. But it will also tell you how much power it requires. And that's another way of looking at how much current it's going to draw. Okay, so the product of these will allow you to figure those out. If they give you the power and the voltage, you should be able to calculate the current. If they give you the voltage and the current, you should be able to calculate the power just by rearranging this equation. Okay, so these aspects are important in your fan choice. And so it's not only about the pressure that your fan generates, it's not only about the flow rate, but your fan also has to satisfy certain voltage and current requirements or voltage and power requirements, because that's going to tell you essentially which batteries you can use when you want to do all of this. So one thing to keep in mind is that a fan is essentially an electric motor with a piece of plastic attached to it that rotates and causes the air to flow in a certain direction. It's really just an electric motor with an appendage attached to it. And electric motors, their speed at which they turn is proportional to the voltage that you plug it into. Okay? By proportional meaning if you double the voltage, you should double the speed. There are some real-world checks there that if you get it going too fast, then friction starts to screw things up. But generally, it's proportional. When you make a certain change to the voltage, you'll get a proportionally equivalent increase or decrease in the rotation speed of the fan. Okay, so hopefully that's pretty intuitive for everybody. The current requirements are non-intuitive for a fan. A fan draws the most current when it's turning the slowest, not when it's turning the fastest. Okay? So in that sense, it's counterintuitive for most people. If you knew the equations for actually, electric motors and fans are actually relatively complicated electrical devices. And you can learn about these details in probably electrical engineering courses where you can actually see the calculation for why it draws the most current when it's turning slower and not when it's turning faster. But that's not really the objective of this course. Rule of thumb that you can keep in mind for this class is that we're going to recommend that you aim for 12-volt motors, 12-volt fan motors. Okay? You can aim for a higher or lower, but 12-volt is a nice number because they tend to be plentiful. They're easy to find. Okay? But that said, just because the manufacturer calls it 12 volts, you can run it at 6 volts. It's just going to run half as fast. Okay? And the fan curve that you use will be a different one. That's an important thing. I'll point that out in a second with the graph. You can also run it at 18 volts. If it's all the specs and all the flow rates are for 12 volts, and you run it at 18 volts, you're like turbocharging it. Right? You're giving it more speed than the manufacturer's graph corresponded to. Now that said, it'll turn faster, your hovercraft will float higher, but all your calculations are just thrown out the window. Now, on the last day of the semester, we will see people say, oh, we had to add so much little stuff to our hovercraft through the semester that our weight is now very different than what it was when we did our calculation back in October. Okay? A quick way to a sleight of hand to fix that problem is to change the voltage level of your battery pack. Buy a new battery pack, essentially. Okay, that's one way to do this. Okay. Fans have a variety of requirements, as I was getting at a moment ago. From the point of view of the operation of your hovercraft, i.e. will it lift up off the ground or not, the issues that you mostly care about are the flow rate of the air that goes through the fan and the pressure that the fan can build up underneath that hovercraft. But as I just said a second ago, the practical realities, you also need to know something about how much energy it's drawing and what voltage it's doing it at. What's going to make your life complicated are that these fans on a typical hovercraft are going to draw about 1 or 2 amps, maybe 4 or 5 amps. You're not talking 30 amps, and you're not talking about 300 milliamps, okay? You're talking about single, maybe up to 10 amps of power are going to be drawn by these things. And that's a fairly large amount of current. This can kill a person if you put it in the right place for the right amount of time, all right? It's actually a fair amount of current. You will know it if you accidentally touch a 12-volt battery pack that has the ability to deliver 2 amps. You'll know it if you short on your hand. It'll give you a really nasty shock. And if you don't disconnect your connection to it, it could do some damage. So pay attention. It's the typical electrocution safety hazards, right? It's not like an electric chair kind of unsafe, but it's gonna hurt, okay? Because these fans draw so much current, and the realities, I mean, the real-world constraints of the battery packs you're probably going to be working with, they're going to be pulling that energy out of the battery pack pretty quick. And what happens, unfortunately, is the battery's voltage is going to drop, right? And when the battery voltage drops, what happens to the fan speed? It drops, all right? And if you follow the chain of logic here, the fan speed drops, the airflow rate drops. The airflow rate drops, well, the hover height will drop. If the hover height drops, you might start dragging and you might actually just settle down to the ground. So as your batteries run dry, you're not going to hover anymore. You've probably seen this in your own experience in life where batteries run down and you can just see the thing slowing down. It's not quite as fast as it was. So all those calculations get thrown out the window unless your batteries are running at the voltage that gave you that flow rate that you pulled off of that graph for the fan curve in the first place. So it's a bit complicated. You can't really do your calculations very easily to handle all possible voltages that your battery will give you from the point when it's fresh to the point where it's just about to stop moving completely, okay? What you have to do as an engineer is pick a reasonable average value. Pick something in the middle. And I'll show you some graphs in a little bit that will help illustrate visually what's happening to the voltage as time passes, as it's powered by the motor, as it powers the motor, excuse me. So batteries can be a fairly complicated topic, and they're actually a very timely topic. Battery technology is advancing extremely fast in the past 10 years or so, maybe the past 20 years. Really, the cell phone world got us to start thinking about batteries a lot more carefully. A lot of engineers that are sitting in the audience here are going to be working on battery technologies in their own careers into the near future, because not only a lot of consumer devices depend heavily on having small, high energy density batteries, but nowadays we're trying to move to alternative energy sources. And one of these, or two of these that are good examples of alternative energy sources are wind and solar. Okay? And two of the biggest weaknesses of wind and solar is that they're intermittent. The sun doesn't shine at night, so where do you get your electricity at night? And the wind doesn't blow all the time. Where do you get your wind? Where do you get your energy when the wind isn't blowing? Well, the vision for what we're going to do as a society and the technologies that we're really trying hard to develop are ways to store energy when we do have it, and that way we can have it in a battery, for example, that we can discharge at nighttime when the sun isn't shining. So you might be able to read between the lines here. A lot of research and development is going in this area. A lot of industry investments are going here to figure out how to make batteries better. And what better means is different to different people. A battery that has to go into an electric car is very different than a battery that's going to power your neighborhood at night because everyone's solar cells aren't getting any sunlight. Okay? So what makes a battery better really depends on what you're using it for. But suffice it to say that across the board, we're trying to make batteries better for a whole lot of reasons. Sometimes it's consumer devices, sometimes it's ways to break ourselves of petroleum or other fossil fuel energy sources. So batteries have a capacity. The capacity of the battery is printed on it if you have, let me back up a second. If you're buying Energizers or Duracells, call them consumer batteries, the ones you'll buy at Walmart or the grocery store, they will never tell you what the capacity of their batteries are. In fact, it's a trade secret. Now, come to my lab and we can measure it for you, but they don't want to tell people this because the numbers can be pretty embarrassing when you compare it to rechargeables. Right? Rechargeable batteries and non-rechargeable batteries, if people knew the details of bang for the buck, you wouldn't buy another Energizer, and this is the rechargeable Energizer. You'd never buy another one the rest of your life. It's almost a ridiculous comparison. But when you're buying rechargeable batteries, they almost always, unless it's an Energizer or a Duracell, they'll tell you what the capacity is. It'll be a number written on it. Here it's 3,000. That is measured in units of milliamp hours, or sometimes amp hours if you have a lot of them. So 3,000 milliamp hours, that's equal to 3 amp hours, okay, is just going to be equal to how much current that battery can deliver multiplied by how long it can deliver it for. All right? So the current multiplied by how long it lasts will give you a total amount of energy. This isn't the power. Remember, power is energy per unit time. This gives you the total amount of energy. Okay? Capacity is sometimes, if you look up, and you guys probably will do this when you're shopping for your batteries, you're not going to take the uninformed consumer approach. Well, if you do, you're probably going to pay for it later. You're probably going to take advantage of what you learned here and look for batteries that have certain characteristics. A capacity, Q, is a measure of how much energy it's got. The bigger this number, the better. Okay? But you also have to pay attention to how many volts that pack is generating. You need to know both of those things. Sometimes you'll see these capacities as milliamp hours. Frankly, most often you'll see them as milliamp hours because these are units that allow you to do quick estimates in your head of how long it's going to last you. You just need to know what the current is, and then you can figure out how long it will last just by figuring out. So 3 milliamp hours will give you 3 amp hours. Will give you 3 amps for 1 hour. It'll give you 1 amp for 3 hours. You can just do the math in your head. Sometimes you'll see these given in units of coulombs, which are the official physics units, if you will, that measure the actual amount of charge being delivered per unit time. It's not terribly useful for quick in-your-head calculations. Okay. So, just to sort of illustrate what I was getting at a second ago here, you can have a battery. This is a typical nickel metal hydride C-sized battery. Current technology, this will deliver 5,000 milliamp hours of energy. Okay? What that means is 5,000 milliamps for 1 hour, right? So, or 1 amp for 5 hours. 5 amps for 1 hour, 2 amps for 2.5 hours, whatever. The product of this number by that number has to add up to 5. Here, I call it 5,000 because that's in milliamps instead of amps. Okay? So pretty easy to read the batteries if they've got the numbers on the side. Okay? This will give you this much energy at 1.2 volts, which is probably not enough to run a 12-volt motor or 12-volt fan. I said that you can run fans at lower voltages and they'll just run at a slower speed. But when you get that low, down to 1 volt, it's probably not even going to turn. But it'll probably, it's reasonable to say that the voltage and the speed are connected to each other. But once you get to about half the rated voltage, then it might not work so well because the friction in the fan and things like that start to overwhelm it. So, as I hinted at a little while ago, the voltage that your battery gives you is actually a fairly complicated question to answer. The number that the manufacturer puts on the side of the battery, you can throw that out the window unless it's a fresh battery. Right? If it says a 1.5 volt battery, odds are you're getting 1.2 volts out of it. The nickel metal hydride here, it's going to say, most likely it'll say 1.25. You take it fresh, you fully charge it, you take it out of your charger, and it says 1.15, not 1.2 like it says right on the side of the battery. And the minute you start using it, it drops down to 1.05, and then 1.0, 0.9, 0.8, right? That's just the reality of the world that we sort of have to live with. So when you do your calculations for batteries, you'll probably actually get the initial charge voltage. If they're brand new batteries, they haven't been used a whole lot, the side of the battery will say 1.2 volts. The first time you charge it, it might actually go up to 1.4 volts. Turn it on, 10 seconds later, it's down to 1.2. Okay, so they can be a little bit misleading unless they're actually running. If you just stick a multimeter onto your battery when it's fresh out of the pack, that's going to give you information that's kind of useless, right? Because it's going to be out of date as soon as you start using it. So the voltage is going to depend on a whole bunch of things, some of which you can control or at least be aware of, and others that you just have to simply live with. The battery voltage is going to drop depending on how much energy you've already taken out of it. Is it 50% charged, 90% charged? Your battery voltage is going to depend on that. I'll show you some graphs later on for typical battery technology for that. The voltage that your battery can deliver will also depend on how quickly you're trying to pull that energy out of it. So if you have a high current motor, your battery voltage is actually going to drop even more. And so that makes life even more complicated. If it's colder, your batteries are not going to have the same voltage. If you've ever done like winter hiking or something like that, and you have your little, even cell phones cell phones are better. They use lithium-ion batteries, which can handle cold temperatures pretty well. But if you had like alkaline batteries in your digital camera and you took it on a hike in the snow or took it skiing with you, and you realize that, well, why is the battery's dead? I charged it right before I came. Well, odds are I just got really cold, and the batteries can't handle that, and the camera is measuring the voltage to figure out how much juice is left in the battery. But the voltage is dropping artificially because of the temperature, so it fools the camera into thinking that the battery's drained. A question out back? The question was essentially, if you keep your batteries in the refrigerator, do they last longer? The short answer is, I don't know. Because it really depends a lot on the chemistry of the battery. Is it a lead acid, a zinc battery, the older ones, alkaline, lithium ion, things like that? One thing that you can keep in mind is, maybe you haven't put these things together yet, but a battery is essentially a chemical reaction. And generally, chemical reactions slow down a lot when you lower the temperature. Okay? So they won't generate much voltage while they're in the refrigerator, but if you take them back out and let them warm back up without having actually used them in the meanwhile, my intuition, my own sense of what I know about these is that it would probably essentially come back to life. But if you try to use it while it's cold, the voltage level drops way, way down to the point where your electronics think there's no battery there. Okay? So short answer is I don't know, what I do know is that it will vary a lot depending on what kind of a battery it is. Question up front? Yeah, so in principle, if you leave your battery out in the sun after you think it's pretty much dead, what happens is the battery voltage goes up, but you better use it while it's warm, because if it cools back down, you don't have that anymore, right? You're sort of faking it out. A lot of these rechargeable batteries, you run your thing down, your hovercraft stops hovering, you take the battery out, and someone says, oh, that couldn't be dead. They put it back in, and the thing powers right back up, and it hovers again. You let the batteries relax a little bit, right? And suddenly it found more energy. Not really. It's complicated. The history of the previous current flow can make a difference, and it's going to drive you crazy because sometimes you can't figure out, is your battery really dead or not? Because it seemed dead 5 minutes ago. I let it rest a little while. Now I turn it back on, and it works for a little while, but it won't really last very long. Okay, so the chemistry of batteries is really what's given credit for why battery technology has gotten so good so fast in recent decades. I mean, this is the guy who invented the cell phone, or at least the guy who's given most of the credit for inventing the cell phone. He's all proud about how small his phone is. This was back when I was in high school, basically, for this. This phone, this is a cell phone, believe it or not. Over half of the body of this phone is the battery. Okay, just the battery. The electronics, I mean, back in the 80s, our electronics they're getting small, but they're nowhere near as small as they are nowadays. And you can kind of compare that to a phone that we have nowadays. You've all obviously seen phones. They're very thin, lightweight, compact, and the batteries last a long time. My first cell phone I got, which was 10 years after this, I could talk for maybe 30 minutes before the battery would run dead. I mean, seriously, that's like 5 or 6 iTunes songs, on your phone. It's not long at all. Nowadays, your batteries will generally last for many hours of conversation, of active use. So not only are they extremely a lot smaller than they were a few decades ago, but they last a whole lot longer, and they're a whole lot more lightweight. Size and weight aren't necessarily the same thing. So the chemistries, what we make the batteries out of, are really what are driving these improvements in the technologies. The old technologies, zinc-based batteries are really the oldest ones. Lead acid are still around nowadays. They can hold a lot. They're very cheap, but they tend to be heavy. These are the chemistries that you'll see in your car battery, for example. They can really deliver a lot of energy, and they can also deliver a lot of current compared to other technologies. Alkaline, this is your typical Duracell or Energizer battery. The major limitations of both of these, well, I take that back. Lead acids are not necessarily one-time use. But the major disadvantage of the alkalines is that you use it and you throw it out. Well, you're not supposed to, right? You're supposed to recycle it. The materials that are in it are actually strategically important materials to the US. Most of the materials that we use in these high-tech batteries, we don't find in the US. That's a problem for national security, for economic security in the future. It's one of the reasons we're putting so much effort into developing new battery technologies. All the really cool batteries we've got require things like nickel or cadmium or other even more exotic materials that we have to buy from China or Russia or other people who are our friends today, but who knows what things are going to be like in the future. We'd much rather have it from common materials that we have available to us. NiCads, nickel cadmiums, are rechargeable. This was the first major generation of so-called high-tech batteries, for consumers at least. Lead-acid batteries are rechargeable, but the NiCads are the first ones that we tended to see in consumer batteries, like the small AA and AAA and D cells and things like that. They're fairly inexpensive, certainly nowadays, and you'll still see these. They're old technology. They do have some benefits, but they're really being phased out by most people. They're inexpensive. That's one of their major benefits. Another major problem is that the third or fourth time you start to recharge it, you realize it doesn't last quite as long as it had been. And by the 20th or 30th time, you're probably only getting half of the run life out of those batteries that you did the first time, right? So that's a characteristic problem of these nickel-cadmium batteries. And the reasons that this happened are closely tied to all the materials engineering that goes on in it. In short, the material changes inside the battery gradually over time. It's not a very stable material. These have been replaced with what are now the current leading technology for consumer-grade rechargeable batteries, nickel metal hydride. Okay? They mid-priced, the prices are coming down dramatically. They're getting to be about the same as NiCad. They're even getting to be about the same as one-time use alkaline batteries. They can hold a whole lot more energy. They last a lot longer as a result of that. And the materials that they're made out of aren't quite so toxic. Problem with nickel cadmium is that cadmium is a very poisonous metal. And it's not dangerous to the consumer unless you cut your battery in half and then suck on it or something like that. We're much more concerned about landfills. People generally are not yet trained to recycle the batteries. Raise your hand if you've recycled your batteries regularly. Not many people are trained to do that yet. Okay, so it's going to become more and more important because the materials that we make them out of are getting more and more expensive. So you're going to want to recycle them. They might actually put deposits on batteries. If you were to buy a new battery for your car, they're going to insist on you giving them your old car battery, right? Nowadays they might actually charge you core charges, but they want these old ones because things like lead, cadmium, other materials in them are generally not good for the environment, and they can actually poison entire areas if too many of these are in one spot. Plus, it just makes more sense to recycle these scarce materials in the first place. Finally, down at the bottom, lithium-ion batteries are becoming more and more common. You'll see them in consumer electronics like your cell phones, your iPads, your laptops, things like that. They tend to be more pricey, but they're much lighter weight, which is important in an iPhone or your laptop. High capacity, meaning there's a lot of energy in a small space and in a small mass. But they have some complexities. The ways that you charge these things are a little bit more complicated. It's easier to have one blow up on you if you don't charge it correctly. Right? We don't recommend you use lithium-ion batteries in this course. Right? Life can get more complicated. You can. It might blow your budget. You'll have some really cool high-tech batteries, and there'll be little dinky things that weigh very little. But if you have any designs on using a lithium-ion battery here, you must talk to me because I have to give you special instructions on extra equipment you have to buy to charge it safely. All right? Most people don't because weight really isn't a major driving factor in the hovercraft designs. You need to know what the weight is, and it can't be ridiculous, but you can get away with nickel metal hydrides quite easily. But we're not going to insist that you do it. You probably are going to want to use them. Okay. For your batteries, the voltage, that's the most obvious one. That's what they sell you the battery based on. It's a 1.2 volt battery or 1.5 volt battery. But now you need to start paying attention to the capacity. And generally, the bigger the battery, is it a AAA cell, a AA, a C, or a D, or an F? You've probably never heard of Fs. It's not a typical consumer battery size. The larger it is, generally the more the capacity is, provided the chemistry is identical. Provided you're comparing apples with apples. Okay? In this class, you're going to be more concerned with things like cost, the peak current capability, the capacity, the voltage. You're much more concerned about these four than how heavy they are, because they're all going to be within a certain range of weights. You can use lithium-ion and cut your weight in half, but it wasn't really too heavy in the first place, so cutting it in half for tripling your cost is usually Usually not a design decision most teams make, but that's up to you guys. Some people just say, I just want to make the highest tech hovercraft we can. And go for it, but talk to us about the safety issues about lithium ion. Or lithium polymer, if you know the difference. Size of the batteries usually doesn't matter. How long you can leave it on the shelf before it drains itself doesn't really matter. These matter to some people. If you're making a battery for a smoke detector or something like that, you don't want it to self-drain in 1 month. Then that darn thing's going to be going off at 3 a.m. every month, right? So you have to go and change the batteries. That's what mine are in my house. Why do they always go off at 3 a.m.? I don't know. It's like they have a timer in them. Maybe it gets colder at night and the voltage drops, making the electron. Yeah, bet you that's it. Yeah. Okay. And then finally, in the real world, safety, environment, and reliability of these things is very important. Apple was making laptops that had their batteries explode 3 or 4 years ago. Not all of them, but a few of them did. And the problem was that the charging circuit that was working with these lithium-ion batteries was causing them to overheat. And eventually, if it gets too overheated, the battery pack actually kind of explodes. And not like the whole house goes down, but if it's on your lap, it's not going to be a pretty sight. Right? So that's a bad thing, right? So developing a reliable technology, a safe technology, and one that's environmentally friendly has lots of real-world consumer ramifications or commercial implications. Lots of different sizes. I'm not going to look at this in detail, but for the same technology, nickel metal hydrides here, AAA, AA, whatever, you can get pretty broad ranges of how much energy they store. 1,000 milliamp hours in a AAA, you can get that for about 90 cents each. A AA battery, this is what more people have for their electronic devices. That'll hold about 2,600 milliamp hours and cost you $1.50 a piece. A 4-pack at Walmart of alkaline batteries, AA, will cost you about $4, $3.75, something like that. A 4-pack of these, and they're good once, okay? And they hold about 2,600 milliamp hours, right? You can pay twice the amount, $1.50 each instead of 75 cents each, twice the amount, and you get rechargeable batteries that are probably good for 50 recharges. So here's where I was getting at, the dirty little secrets that the battery companies don't want you to know. It's almost no comparison. You get one use for 75 cents or 50 uses for $1.50. You do the math, okay? Your team should do the math when you figure out, do you want to use rechargeables or not, okay? It's a no-brainer, okay? You find that the amount of capacity that you have and how big the battery is, a C cell, a D cell, does not scale with cost. It doesn't make sense. Like a D cell battery will hold, say, 4 times more energy as a AA, but it costs more than 4 times more. Right? So be aware of these types of things. When you shop for batteries, you can look at these types of numbers. Okay. For the same size batteries, but the different chemistries, alkaline batteries, about 2,800 milliamp hours, NiCad, nickel cadmium, a little bit less. These numbers are better than this nowadays. Nickel metal hydrides, I'd say for a AA, a good number is probably 2,600. You can get really cheap ones that'll only give you 1,300. You can pay $4 each instead of $1.50 each and get 2,900. A good cost-effective middle ground is about 2,700, about the same as the alkaline. Lithium ion, you'll get a little bit more, right? So lithium ions, you don't get a whole bunch more energy. You'll get you tend to get a higher cost, and you get a lower weight, and you get better low-temperature performance, which for some cases really is a big deal. Like if your car won't start when it's cold out, that would suck, right? So temperature performance does matter for those things. Okay, not all batteries have the same basic cell voltage, 1.2 volts for NiCad rechargeables. Alkalines, 1.5. Lithium technologies, there's a lot of lithium technologies. Most of them are over 3 volts. You actually have some in the 1.2 volt range also. Lithium iron phosphates, I think, are about 1.2 volts. All right, I already kind of mentioned these. I'll go these. I don't recommend alkaline batteries in this class. Nickel cadmium, I'm just going to go through these quickly. We're running a little low on time here. I want to talk about some of the basics of how to combine batteries. When you buy a battery, it says 1.2 volts, right? You need 10 volts for your fan, or 12 volts. How do you get that voltage up? Well, we can combine batteries in 2 different ways, series and parallel. Series ways of combining them, parallel ways of combining them mean that you're attaching the batteries, all of the positive terminals get attached together, and all the negative terminals get attached together. When you add them together like this, the amount of current that the battery can deliver will go up by a factor of 4, but the voltage will still be 1.2 volts. Right? In parallel, the voltage stays the same as the individual cell. In series, it's the other way around. So parallel, going back 1 second, the currents add up. How much current the battery can deliver will add together for each cell you add. 10 cells will give you 10 times more current. Okay? When they're in series, which means now that the positive of one gets attached to the negative end of the other. Positive one. So you're adding them one after another, electrically speaking. We call that in series. In this case here, the voltages add together. So if you have 4 of them, you have 4 times the voltage of one of them. So 4 times 1.2 volts gives you 4.8 volts. Okay? Question? You can't easily switch them, but you can combine them. All right? So you can have mixtures of some batteries that are in parallel, some that are in series, and I'll get to that in a second. Okay? It's actually a clever way to get what you need in this class. Okay? Important or interesting thing to note, if you've ever seen one of these 9-volt batteries, right? These individual cells, their voltages are 1.5 volts. How do you get 9 volts? Well, if you were to bust one open, you'll see there's actually 6 volts, 6 cells in there. And they're all wired together in series so that their voltages add up. 6 times 1.5 volts gives you 9 volts. All right? You wouldn't know that. When they show it to you from the outside, it's called, incidentally, this is a battery, this is a cell. A cell is one individual electrochemical circuit. Right? Don't worry about those details. A battery is a cluster of them. That's what the battery really means. You can have a cluster of 1, a battery of 1. It's also a cell. Okay? So, clicker question. Are these batteries here in series or in parallel? All right, or both. How I drew the picture is not the key thing to note. Well, let me rephrase that. The fact that these two batteries are parallel to each other is irrelevant. I could have arranged them any way I want on the page. Okay, running out of time here? All right, they are in parallel. Okay, what that means is that they are electrically in parallel. Parallel batteries have all of their positives attached to each other and their negatives attached to each other. Okay? That was in parallel. Important safety reminder. These battery holders, they generally allow you to combine batteries in series, usually. You can get some that are designed for parallel. They allow you to put, like there's 8 slots. You get 8 batteries, and it'll give you your voltage 8 times higher, usually. Do not use these in any way in this class. They melt. Your fans are going to draw way too much current. They're going to overheat, and they will melt and catch on fire. So do not use them. I'm not exaggerating. We have things catch on fire because of this reason. Okay? So I will finish this calculation, or maybe Dr. Volstead will, next class. Are there any questions before people take off? Okay. We'll see you on Monday.